Hello guys. In few of the videos before we discussed about the donor electrons and or n-type semiconductor and then acceptors or p-type semiconductors. There, if you remember, we discussed about how the donor energy level is very close to the conduction band, and the order of the you know this gap here, okay, the order of the energy gap between the conduction band and the donor energy level is very less, we said, and we said it is 0.01 electron volt, whereas the band gap is approximately of the order of 1 electron volt. So if you will compare this value, I mean 1 electron volt and this value, this particular gap between EC and ED is very small, and that's why we said by a small thermal agitation the donor electrons can be elevated from the donor energy level to the conduction band, right? But when I said approximate value, okay, is this, and the second thing we said, the donor electrons here, okay, these extra electrons or excess electrons that you got, which will be elevating to the conduction band by thermal agitation, because the amount of energy required is very less. Okay, these donor electrons are loosely bound to the pentavalent impurity that you are adding to intrinsic semiconductor or silicon or germanium, we said. Now the question is, what is that exact value here? Okay, the amount of energy required for the electrons to move from ED to EC, right, donor energy level, to the conduction band. Okay, so this is known as ionization energy. So how we will define it? So we will just define the approximate energy required to elevate the donor electron into the conduction band is known as the ionization energy. So here we are going to do a small mathematical derivation to know what is approximately this value, right? This gap between EC and ED. First thing is that, and the second thing, we as we said, this donor electron is very loosely bound to the atom, okay, to the pentavalent impurity, right? So how loosely it is bound? Can we just quantify it? Can we derive a mathematical value for that? So two things we will try to find out. So how this donor electron is loosely bound to the impurity atom. The second thing we are going to find out is the ionization energy, that is the amount of energy required to elevate the donor electron, okay, from the donor energy level to the conduction band. Okay, so for this I'm going to take a very simple mathematical model. Okay, so what is that mathematical model? So when we said when electron is leaving the donor energy level, it will leave a immobile charge. So right, so immobile ion E plus, and you got this is electron. So here you got the ion, actually this is your phosphorus ion, where you got this ion over here is this, okay, that's the donor impurity you added, and the electron which is elevated to the conduction band. So this corresponds to a specific energy, and if you will consider a simple mathematical model, okay, like this, that the electron is considered to be in a particular orbit, a specific energy level, and is revolving around this this particular ion, impurity ion. Here it is phosphorus, for example, you took the pentavalent impurity, and it is revolving, so that I can use a simple mathematical model to derive the ionization energy quantitatively, and also I can derive a quantitative value for like how far actually this electron will be from this ion, so that I can say that this electron is actually loosely bound to this impurity atom. So this is our objective, and in this video we are going to find out that. So if you'll see here what is the force of attraction between this positive charge and negative charge, and the Coulombic interaction, we can say. And this Coulombic interaction actually provides the necessary centripetal force to this electron to revolve around this particular ion, right? So we will consider this, right? So this positive ion and the Coulombic force between this positive and this electron, positive ion and the electron here, okay? And the Coulombic force actually provides the necessary centripetal force, okay, to orbit, okay, here, okay? So if you write that the Coulombic interaction, as we know, the Coulombic force can be written as, the magnitude, product of the magnitude of the charges. So here you got E and E magnitude, as I said, so E square divided by, you got 4 pi, and let's take the medium here, is silicon inside, so I will take the electric permittivity of silicon. And then let's just to generalize it, I don't know, suppose it's in the nth orbit, so I will write it as, just to generalize it, I will write it as Rn. Okay, Rn is the radius of the orbit. Okay, and this square. Okay, now this can be equated to the centripetal force. This I'm writing for Coulombic force. Okay, and the centripetal force required must be written as m, I'm putting a star over here, v square divided by Rn, right? What is that m star? M star is the effective mass of the electron, okay, in the conduction band, because we said the electron actually is elevated from the donor energy level to the conduction band. So now we need to consider the mass of the electron to be what? The effective mass of the electron in the conduction band. You can refer to one of the videos that I have made about effective mass of the electron, and its properties and all, everything is discussed there. So you can please refer to that as well for more understanding what is effective mass. So effective mass of electron should be considered in the conduction band. Here v is the magnitude of the velocity with which the electron orbits. Rn, as we have already discussed, this is the distance, or the radius of the orbit. Okay, so now here in this case we can now write, as we said, the Coulombic force provides the necessary centripetal force. We can equate this. So E square divided by 4 pi epsilon Rn square can be equated to this effective mass of the electron in the conduction band, and V square divided by Rn. So this is what we can write. Okay, so we will start with this basic equation, right? Before that, what we can write, we can use the Bohr's model here. So what is Bohr's model? Bohr's model says that if the electron is actually revolving in a particular orbit, its angular momentum must be quantized. Okay, so if we'll assume that the angular momentum is quantized, then we can write angular momentum in terms of linear velocity, and this r we can write. Okay, so I will write this as, m star, okay, effective mass of the electron, and Rn, okay, and then this V. So angular momentum, okay. So angular momentum, actually this is r cross p. We are considering the only the the magnitude of the angular momentum. So r cross p we got. So p is your linear momentum mv, and then r. So I'm just writing the magnitude over here. So m star Rnv must be equal to nh bar. We considered the angular momentum is quantized. Okay, angular momentum is quantized. This is what the Bohr's model says, right? Then only the electron can revolve without radiating any energy, right? So m star Rn v equals to nh bar, or else if I'll just take out what is, make v as the subject, which is velocity, can be written as nh bar divided by m star Rn, right? Now you take this v value and substitute in the equation, this equation v for v square, right? Okay, I'm just clearing it. So let me write this way. So what we got, the Coulombic force, which we wrote as E square divided by 4 pi epsilon. This is electric permittivity of silicon, as we have considered the intrinsic material, the host material is silicon, then is equal to m star, the effective mass which was there. Okay, I'm substituting for v square. Okay, so v square I will substitute as n square h bar square divided by, okay, we got m star square and then Rn square. What we substituted? We substituted v is equal to nh bar divided by m star Rn, right? So now you got this, and then you have this 1 by Rn, or Rn is already there. So mv square divided by Rn. Okay, so this. Now from here you can just, you find out what is Rn square, solve for Rn. Okay, solve for Rn simply. You can see here Rn square and Rn square will be cancelled, and you can make this as the subject and find out Rn. So we can write this Rn as what? You got your n square h bar square, Okay, then you have this 4 pi epsilon over here. So I will write that 4 pi epsilon divided by m star, and then you have E square over here, m star and E square. You got, m star and this cancelled, so you got finally this. So you got Rn is the orbit, the radius of the orbit, right? Or the radius of the orbit. So now here, if I will just substitute some values, like for example, if I will consider this epsilon, okay, this is for silicon we wrote, okay, the orbit where the, the donor electron is actually revolving around the impurity atom. Okay, so we can find out what is that value actually. Okay, let me just take, okay, if I'll take this, the same thing for free space, what I will write, epsilon uh, will be replaced by epsilon naught. So we know the value, it is 8.85 into 10 to the power minus 12 SI unit, which is Coulomb square, Newton inverse, and meter to the power minus 2. Okay, and the value of H also is known. So H is 6.626, so 62, for example, 10 to the power minus 34 joule second, right? Joule and second. Okay, then m0 is the rest mass of the electron, which is 9.11 into 10 to the power minus 31 kg, right? And then E value, the charge of the electron, magnitude of the charge of the electron, 1.6 into 10 to the power minus 19 coulomb. So these are the values. If I will substitute all these values here for free space, okay, then we can write what is this Rn. And for example, I will write this, n is equal to 1. Okay, I will substitute for n equals to 1. Okay, n equals to 1, and with all these values, epsilon naught, h, and all. Okay, so we can write the Bohr radius. Bohr radius, so this Rn is Bohr radius. Okay, that's the most probable state that electron will occupy. Okay, that's a Bohr's radius, which can be written as, I will write this 4 pi, the same value that is given here, 4 pi. Epsilon I will write as epsilon naught, okay, which is 8.85 into minus 12. Okay, and then n equals to 1, so 1 square gives you 1. H bar square here, h bar is h by 2 pi, so you can substitute this 6.62 into minus 34 for h. So let me just write this way, h bar square divided by m naught E square. So you use all the data given over here, and then you calculate. The value is found to be 0.53 angstrom. Okay, 0.53 angstrom. Angstrom is what? 1 angstrom is actually 10 to the power minus 8 centimeter. Okay, 10 to the power minus 8 centimeter, or you just write it as 10 to the minus 10 meter in meter if you right. So this is the value for n is equal to 1, right? For n equals to 1, this is the first orbit, or the most probable state for the electrons. Okay, quantum mechanically also you have verified that the a0, or the Bohr's radius, is defined to be the most probable state, right? So now we got this 0.53 angstrom. Okay, for free space. Okay, and considering n is equal to 1, and Rn we wrote here for silicon, right? Now if we'll take the ratio between Rn and a0, whatever we calculated, we wrote. Okay, Rn, let me write again, n square h bar square 4 pi epsilon divided by m star, effective mass of the electron in the conduction band, E square, multiplied with a0. So 1 by a0 I will write, so that gives me m0 E square. Okay, divided by 4 pi epsilon 0, n is equal to 1, so you got h bar square, right? So this can be rewritten as n square, this is m0 by m star. Okay, then epsilon divided by epsilon 0, right? Which can be written as n square. This epsilon by epsilon 0 is nothing but the relative permittivity, electric permittivity. So we can write this as epsilon r. And what we got, the ratio between m0, rest mass of the electron, and m star, effective mass of the electron in silicon, or in the conduction band of silicon, right? So here these are the things, right? Now for lowest energy state, if I want to write, okay, so lowest energy state, okay, energy state, if I'll substitute n is equal to 1 for lowest energy state, if I'll substitute n is equal to 1, Okay, and for silicon, if I am writing for silicon, the value of epsilon r relative permittivity is around 11.7, right? The ratio here epsilon by epsilon naught is this, right? So if you will calculate, substitute these values here, okay, and find out, like, okay, and then another thing, what is m star by m0, that is the ratio between the effective mass of the electron in the conduction band of silicon and m0 rest mass of the electron. This also gives you 0.26. This is the value for silicon, right? Then you substitute all these value and n is equal to 1 here. So I can write r1 divided by a0, if I'll write, okay, r1 divided by a0, that gives us the value 45, right? This implies we can write what is our r1. R1 is actually n equals to 1, the lowest energy state we have taken. So lowest energy state, if I'll take n is equal to 1, this radius, okay, this radius, the radius um, of this electron from the ion over here, right? The distance, that we said it is revolving, right? So this distance we consider for lowest energy state, this should be r1, and we can write this to be what, whatever we calculated for a0, which is 0.53 angstrom multiplied with this 45, that gives us a value 23.9. Okay, a0 times 45, a0 was 0.53 angstrom, so you multiply 0.53 with 45, this angstrom we got. Okay, this is is 45 times your a0, which is 0.53 angstrom. So 23.9 angstrom we got. Okay, so 23.9 angstrom. Now what this value actually gives us, so we got r1, the distance of the electron from the phosphorus or the pentavalent impurity, it was found to be 23.9 angstrom, okay, which is approximately 4 times, okay, the lattice constant of silicon. Lattice constant of silicon. So what do you mean by that? Lattice constant of silicon, that means silicon atoms, if you consider like this, okay, so they are periodically arranged. For example, this the average distance between these molecules, these atoms, actually gives you what, a. Okay, a is nothing but the lattice constant, okay, or lattice constant, here I wrote it for a. Okay, so 4 times this gap you got, right? So 4 times this gap. So if I will consider the phosphorus atom here, somewhere here, this is silicon you have, okay, and then silicon in the crystal because you doped it, right? So phosphorus, then you consider, like, these 4 times, you consider 4 times this distance, okay, so 4 times the lattice constant, okay, then at this distance this donor electron will be, right? This is the distance, right? That's why we said actually this is, so the donor electron is not tightly bound to the donor atom. So we got, this is 4 times, approximately 4 times the lattice constant of silicon. That's why we said it is loosely bound to the donor impurity atom, right? So this is one thing we discussed here. Okay, one thing is confirmed, that it is loosely bound. Then the second thing we wanted to discuss is the energy gap here. So we said the donor energy level is here, the conduction band over here is this. So this gap is of the order of 0.01 electron volt. Let us find out a better or approximated value. What is this for silicon actually? Okay, so which we said ionization energy. So a simple mathematical derivation can be continued from whatever data we have already obtained for, like, velocity and the Rn value. So we can use those to find out, this ionization energy, or this amount of energy that we got here, ec minus ed, what is this value actually, which we said is the ionization energy, right? Okay, so now if I'll write the total energy of the orbiting electron, okay, around that impurity atom. So we can, I'm just writing E is the total energy, T for the kinetic energy, V for the potential energy. So I can write T for kinetic energy, this is half, okay, m star V square, because it's inside the conduction band. M star is the effective mass of the electron in the conduction band of silicon. So this is what we can write. Then we wrote, like, using the Bohr's model, The angular momentum is quantized, so m star Rn V must be equal to nh bar. So from which we have already calculated V is equal to nh bar, can m star Rn we can write this way, right? So you got Rn, I can write as what, n square h bar square. This is also we have already derived, I'm just rewriting it, divided by m star E square, right? So these are the things. So we can write again, I'm just rewriting, V equals to nh bar divided by m star, and then for 1 by Rn over here I'm going to substitute this value, okay, which I can write as m star E square divided by n square h bar square and 4 pi epsilon, okay. So which we can write as E square, you cancel whatever you can cancel, m star got cancelled, n and this h bar and then this, okay. Write the final whatever you got, nh bar 4 pi epsilon. So we got the V here in terms of E square nh bar 4 pi epsilon, right? So now I will rewrite what is the kinetic energy, which is half m star V square over here, sorry, okay, half, and then m star and V square you wrote, and 1 by 2 m star, and then substitute this value of V and then make it V square. So we can write it as E fourth divided by whatever n square h bar square and then 4 pi epsilon whole square, right? So this is what we got for uh, the kinetic energy. The same way we can write for potential energy. So if I'll write it for potential energy, okay, let me just clear it. Potential energy, if you write, then similarly potential energy I'm writing this way. So potential energy is what, you got the charge, one is minus E, the other is plus E, so multiply minus E square divided by 4 pi epsilon, and the distance between them is Rn. This is potential, right? So we can minus E, we can write it minus E square 4 pi epsilon, okay, and 1 by Rn, the same thing we have, like, we wrote for Rn is equal to n square h bar square 4 pi epsilon divided by m star E square. This is what we wrote for Rn, and I will substitute it as 1 by Rn. So 1 by Rn means what, multiplied with m star E square divided by this n square h bar square 4 pi epsilon, okay. So now we can rewrite m star E fourth divided by n h bar square, and you got 4 pi epsilon square, okay. Now if you write total energy, E is equal to T plus V. So T value we got 1 by 2 m star E fourth divided by nh bar square and 4 pi epsilon whole square. This was value for T we determined, and minus, this is for V, we got n h bar square 4 pi epsilon square. You can see almost the same thing here. You got minus 1 by 2x minus x, right? So this is minus x plus x by 2. So that will give you what, minus x by 2. So 1 by 2, right, whatever we got here, m star E fourth divided by n h bar whole square, and then we have 4 pi epsilon square. So this is what we got total energy for total energy. So total energy is 1 by 2 minus 1 by 2 m star, effective mass of the electron in the conduction band, E fourth electronic charge to the power 4 nh bar square, and 4 pi epsilon. Epsilon is the electric permittivity of the host, okay, like here we said silicon, right? Let us now substitute these values, like we wrote m star E and h, we know, right? And for lowest energy, if you write n is equal to 1, and epsilon, just now we said the value of epsilon, okay, epsilon divided by epsilon naught, that is also known, which is 11.7 for silicon, right? M star by m0. So all these values that we used earlier, we are going to, we can substitute all those to write what is the total energy, right? So I'm just rewriting it again. So what we have, epsilon value is known, 8.85 into 10 to the power minus 12, okay, Coulomb square Newton inverse meter minus 2. H value I said is known 6.62 into 10 to the minus 34, the SI joule second, right? And M0 is known 9.11 into 10 to the power minus 31. E is known 1.6 into 10 to the power minus 19, sorry, minus 19 Coulomb, right? And in addition to that, we discussed what is epsilon r, which is the ratio between epsilon r is equal to epsilon divided by epsilon naught, which we said this is 11.7, that is known. And for silicon, we said m star by m0 is also known 0.26. So you take all these values, okay, and for lowest energy state, we took n is equal to 1, right? So for lowest energy state, we took n is equal to 1. Now you substitute all these values, okay, in the expression for kinetic energy, in the expression, in the expression for total energy that we determined, right? So if I'll substitute it, for E is equal to 1 by 2 m star E fourth divided by n h bar square and 4 pi epsilon square, okay, we will get, if I will substitute for silicon, it gives us minus 25.8 milli electron volt. Okay, so 25.8 milli electron volt. Okay, or you can just, you want to write in terms of electron volt, minus 25.8 into 10 to the power minus 3 electron volt. So you can see, like, 2 and then minus 0.0258 electron volt. Okay, so this is the value what we got, total energy of the electron that is orbiting the impurity atom, okay, and which is there in the, I mean, in the conduction band. Okay, E is equal to minus 0.0258 electron volt. This amount of energy is required, okay, for the electron. This amount of energy is required for the electron to move from the donor energy level to the conduction band. And this value, if you see, this is very, very less than the band gap energy of the silicon, which we said around of the order of 1 electron volt. So if you will compare this, this is very less than the band gap energy of the silicon. Okay, so this energy is the ionization energy. This energy is the ionization energy of the donor atom. Okay, or we can say the amount of energy required to elevate the donor electron into the conduction band. So in this particular video, I tried to explain you, like, mathematically, using a very simple model, both the Bohr's model, and considering the angular momentum is quantized for the electron which revolves around that ion. So considering that simple mathematical relationship, we could estimate, like, what is the order of, or what is the magnitude of the, um, ionization energy, the amount of energy required to elevate the donor electron from the donor energy level to the conduction band. And at the same time, we can also estimate, like, what is the distance actually, okay, the electron exists from that impurity atom, so that we can say, actually, relatively it is loosely bound, not very tightly bound, and by a small agitation like of this order, 0.0258 electron volt, it can actually move to the conduction band. So thank you so much, this is it. um, Please subscribe the channel. Thank you.